Hello, welcome to lesson 1.3. We are in unit B, the chemistry and the environment. In this lesson, we're looking at the impact that acid deposition has on ecosystems. And you can see we're going to be also talking about buffers in this lesson and how they keep constant pH for us when an acid or a base is added to a system. We're going to also be looking at why it's important to keep a constant pH in a living system, and the impacts on the biotic and the abiotic components of our environment that are caused by acid deposition. So you can see our textbook pages that I'm referring to in this lesson, which I strongly suggest reading, and that's where you'll find the practice questions as well. So this little bit at the beginning here, the first few slides, is going to be a bit of review from our very first lesson, and then we're going to add to it a little bit as well. But you're going to see some new terminology and a couple different pieces of information along the way that are new. So we're going to look at emissions and the wind patterns in Canada. So first off, just reviewing what emissions are. So emissions are those gaseous or gaseous products, pollutants that are released into the air, especially when we're talking about combustion, right? So these are the emissions that are coming out of our tailpipe or our factories, and they can be carried by the wind. And so can these particles, right? There's particulates. Remember those really very small solid particles that are also released in the air during combustion? Dust, ash, smoke. There is something called the jet stream in Canada, and it flows from west to east. So emissions that we produce here in Alberta, a lot of them, not all, but a lot of them are actually carried east on the jet stream. So a lot of the times, we might burn something, or emissions will go into the air, and they don't fall down as acid rain until they hit Ontario or Manitoba or Quebec. So this is why acid deposition is actually a national problem as opposed to just a provincial issue. So as we talked about earlier, acid deposition, these are these airborne molecules that when they meet atmospheric water, so water in the atmosphere, they form an acid. And if they're meeting water in the atmosphere, then you can get rain, which is wet deposition or acid rain, or they can actually fall to the ground too as solid particles or gases, and we call this dry deposition. So you can see there's the acid particles and gases just falling. You might also get wet deposition with acid rain or snow here as well. And they typically have a pH of less than 5.6. And just to review, there's sulfur dioxide and there's nitrogen oxides. And both of these are the major sources of acid deposition. So acids, as we did mention before, can be made spontaneously by nature. So you'll get a lot of sulfur oxides formed or released into the atmosphere through volcano eruptions or hot spring emissions. You'll also see nitrogen oxides being released during forest fires. Now, the biggest source right now that seems to be making the largest difference is the anthropogenic sources, and these are the human sources. So anthro always means human, so human-caused sources. So these are pollutants. When pollutants arise from not natural means. Sorry, we're talking about human activities in this case. So the burning of fossil fuels like coal, natural gas that have high sulfur contents, that's where you're going to get the sulfur dioxides. So when we're looking at sulfur dioxides, we're really seeing most of them come from industries. So refining crude oil sands, that kind of thing, refining metals. Whereas the nitrogen oxides, they're mostly from combustion in cars, right? So because you have this high combustion at high temperatures happening with nitrogen in the air, that nitrogen is getting pulled in and combusting when we're burning our fuel in our car or our furnaces in our home. So this is where the nitrogen oxides are coming from mostly. So now we're going to take a look at the effects of this acid deposition. So we know how it's created. We've looked at that quite a bit, the reactions that are happening. But what are the effects of acid rain on our environment and our non-living things? So remember, in our ecosystems, we have biotic, which are the living things in the system, and you have abiotic, the non-living things. So on this picture, you'll probably recognize a few different features here. So if we're talking about the abiotic environment, acid rain really increases the speed that rusting or corrosion can occur. And you can see the effects on some of the rocks as well. And we're going to look at the effects on soil too in a second, and different nutrients and chemicals that are pulled out of substances when acid is present. You can also see a fish, because they're living in an aquatic environment. They're very sensitive to changes in pH in their lakes or oceans. So they're actually a species to watch when lakes are becoming more acidic, because you'll see a lot of die-offs of different species. Some species are much more tolerant than others, so you might end up with lakes with like catfish, a lot of catfish species, because they tend to be a bit more tolerant to acid than other species. You'll also see this discoloration in trees because the chlorophyll is affected, and we'll talk about that on another slide. And then we have these affecting specifically human race. So we're talking about asthma and bronchitis being increased by these acid rain and emissions. So this is just a little a slide about, can you read this graph kind of basic thing, and then from this graph we can figure out what nutrients are most available in acidic soil. So if we're looking for acidic soil, we should be looking, here's our pH, and we should be looking down at this end here. This is the most acidic end, right? So if you look along these nutrients, what's most available, there's very little potassium, a bit more sulfur, like no calcium. Iron, lots of iron. You can see a large concentration, a lot of iron would be present in an acidic soil, but not very much of the other different nutrients that plants need to grow. So iron is available in the acidic soil, but not many of the other nutrients that plants would need to grow, as you can see along here. So if we're looking at the alkaline soil, alkaline equals a base, so just another word for a base. So over at this end, this is our basic end of the spectrum. You can see there's quite a bit of potassium available, sulfur, boron increases weirdly here, and molybdenum is also available. So there's different nutrients are going to be available at different pHs, but plants need all of these nutrients. So if you can keep your soil in the general area where they can get most of the nutrients, the better for those plants. So what happens when they can't get their nutrients? If the pH drops too much, those plants find it really difficult to find the nutrients that they need for their root system. So that's where the roots are, that's where the plant is getting its nutrients. These are through the soil. So if the soil doesn't contain them anymore because they've been washed away or leached out of the soil by the acid, then the plants have nowhere to turn to get them. So this is an example of a plant that cannot get enough iron, magnesium, or zinc, because those substances are required for the chlorophyll. And when you have a lack of chlorophyll in a plant, the plant starts to yellow like this. So you need the nice green is a sign that there's enough chlorophyll in that plant. So that's a sign that this soil is missing some vital nutrients. So the yellowing. All right, so I use the term leaching, and this is leaching. It's kind of like washing away or dissolving. So you can, if you have acid rain, it can lead to the leaching of toxic metal ions into the soil, out of things where it would normally not be leaching. So the example here on the slide is aluminum, and usually it's found in the form of aluminum hydroxide. That's what it looks like there, the formula, and it's found in rocks and soil, and it's just staying there usually. It says it does not dissolve in water very easily. But when you have hydronium ions, aka acid, acid rain, high acidic content. Then when acid is in contact with this, it produces the aluminum ions. So it's coming out of this compound. These aluminum ions are going to decrease the growth of roots, and you can see that in this diagram here. So at a pH of 6.5, no problem. Those roots are really long. You get down to a pH of 5.2, and they are stunted roots. They're not growing very well at all. So too much aluminum in that dirt is going to decrease the growth of roots, prevent absorption of calcium, reduce populations of soil bacteria that are really important for decomposing. It just affects and messes with everything, basically. All right, so some of the effects of acid deposition here are summarized. We talked about a lot of these ecological impacts. The acid can wash away soil nutrients, and then it can also bring in leaching in of like fertilizers and metal ions that wouldn't normally be in the soil. So we talked about the soil changes in the soil pH that can affect the plants and bacteria. We talked about the death of aquatic fish, which actually impact the whole food chain, right? If they're near the bottom of the food chain. Defoliation, so the losing of the leaves. So when they're discoloring, they will die and actually fall off. And then there's also some societal impacts too we should talk about. There's the corrosion of buildings, monuments, statues, bridges. Also the dry deposition, so those emissions have increased the rates of asthma and bronchitis quite dramatically, and you'll be watching about that in a video. And all of these negative impacts affect the whole ecosystem, right? Because they're going to reduce the diversity. So there's going to be less species, less types of species in that, and all the populations are going to feel them and all decrease, right? Which in turn decreases the genetic diversity in the population. So there's a lot of effects down the line from acid deposition. So in Alberta lakes, one thing about Alberta lakes is we're quite lucky because there's a lot of calcium carbonate, or limestone as it's also known. So this gives the lakes a slightly alkaline or basic, right? So it makes them a little bit basic. And this is because a long time ago, way back in the Cretaceous period, there was an ocean all over Alberta. You can see it was covered in ocean, and there were coral reefs, and those coral reefs are made of calcium carbonate. So when the reefs eventually went away and the ocean went away, it left and formed sedimentary rock called limestone. And it's found underneath Alberta's soil in a lot of places, and you can see there's a lot of fossils when you go around looking for them. So why is this helpful? Well, because limestone can act as what's called a buffer. It has these carbonate ions, which you would see from this compound. Here's our calcium carbonate. So when this went into water, you'd get calcium ions because it's an ionic compound. It's just going to dissociate, and you would get carbonate ions. It's these carbonate ions that act as a buffer. And so if you add any acid to this, they will neutralize the acid. They can accept a proton from hydronium, right? And they can form hydrogen carbonate like that. Okay, so which basically neutralizes the acid and helps keep the pH of the lake a bit more consistent. Unfortunately, lakes in the Canadian Shield, so like Manitoba, Ontario, and Quebec, they have bases more formed of granite, and those are silicon compounds that don't react with acid at all, and they have no buffering capacity at all. So when they have acid rain fall into their lakes, the lakes become more acidic. They don't have any kind of way to neutralize that acid that's falling in the lakes. So not only do they have the jet stream sending a lot of our acid depositions eastern ways, but their lakes are also not protected by the limestone bottoms that our lakes have. So I mentioned buffering on the last slide, and buffering is basically the idea that if you add an acid or a base to something, you have a buffer in there and it'll help prevent the pH change. Okay, so in the terms of Alberta's water, we're talking about this carbonate ion being present because of the limestone. And here's your reaction if an acid was added, like in acid depth rain, to the lake that happens to contain carbonate ions in the lake. All right, this would be from the acid rain or acid deposition. The acid here is going to donate the proton to the carbonate, and that's hanging around in the lake water. Makes the acid become just good old water. So it's now neutralized. This is our conjugate base, right? We started with the acid. And then the carbonate ion that took or accepted that proton from the acid is now hydrogen carbonate or bicarbonate ion, which is now our conjugate acid. It is an acid still, but it's much weaker than the acid that was coming from the acid rain. So it'll still reduce the pH, will still go down because we are creating a weak acid, but it's not going to go down as dramatically as it would in a lake with no buffering capacity. So we say our lakes in Alberta have a high buffering capacity because of the limestone. All right, so alrighty. Buffering also happens in living systems. This is all over the place, actually. But another example that you should be aware of is in the human circulatory system. So we just finished studying that. There are carbonic acid and bicarbonate ions in our blood. All right. Each of these works to counteract any extra acid or extra base that might show up in the blood. If you have too much acid, it'll react with the bicarbonate ion. If you have too much base, it'll react with the carbonic acid. And they'll both work to neutralize that extra added acid. Because if your pH is not maintained constant in your body, then your enzymes stop working. The enzymes have very specific pH thresholds, and if they aren't working, then your body you'll probably die, actually. But anyway, yeah, you need to keep a certain pH level. Yeah, so we talked about that. The amount of acid that can be neutralized in soil or surface water is called the buffering capacity. So the more a substance can buffer, the higher the buffering capacity. And that is the end of this quick lesson today. Go work on your practice questions, and if you have any problems, make sure you contact me.